I was roaming about the internet and I found this blog post by Vlad Feinberg on how to land a Frontier Lab job, a topic in which I'm quite interested. So this guy works at Google Brain as a Gemini pre-training area lead. Cool guy, cool blog post. Um, yeah, lots of useful stuff. Um, but what caught my eye was this exercise that he left. So today I'm going to walk you through how I solved it. What challenges did I solve? Yeah, what was used, and how I approached this task. So the exercise is quite simple. Code a 10 million transformer model only using JAX-Flex optax, which is obvious since the guy works at Google, right? These are Google libraries. Hard-coded to accept digits 0 through 9, space, plus, and equal sign. Generate a dataset, simple up to 3-digit numbers, have it learn addition. And there's some other stuff like derived chinchilla laws for this, something about dense and memory architectures. Yeah, there's a lot of stuff, but for today, I only want to focus on this, on the exercise itself. So I have already solved it, and today I'm going to just show you how I solved it, go through the code, go through the, thinking on a whiteboard. Yeah, so let's go. Here's my whiteboard. And to start, I think it's best to approach such tasks as you would approach any other algorithmic task. So let's write out what we have to do. We need to build a about 10 million uh, parameter model, transformer model, transformer. Should have used text, but yeah, just because my handwriting is terrible. 10 million for model. What else? Hard-coded to accept digits. So hard-coded to accept digits 0 through 9, plus a space. I'll mark it like so. Space plus an equal sign, and have it learn addition. Okay, sounds kind of simple, but let's tackle this task one by one. Yeah, generate a data set, but that's simple. Yeah, generating such a data set is quite simple, but I should mention that have it learn addition, add up to 3-digit numbers. And since we don't have a negative sign here, let's also say that add up to 3-digit positive number. Let's including 0. Okay. So again, I've already solved this task, so I'm just going to walk you through my thought process and what do we have to do. So first things first, we're working with a transformer model. So we need to define what's our token, what's our sequence length, and how I'm going to pad it, and stuff like this. So let's discuss. First, let's think of some like an example equation that we might encounter. Say 1 plus 1. Right? We want our model to learn 1 plus 1 and predict the answer 2. Something like 1, 2, 3 plus 4, 5, 6 is going to be 5, 7, 9, I think. Yeah, 579. 579. Also, something like 9 plus 10 should be 19, sorry. And also something like 999 plus 999 will result in 1998. Okay, what does it tell us? What kind of use we might get from these examples? So first, I think it's quite obvious that we'll be working with tokens of length 1. It's quite beneficial for us to just define our token as one character, right? Because our vocabulary is quite limited. We only have 13 unique symbols. So might as well keep one token size 1, right? Also, the maximum sequence length is going to be when we add a 3-digit number to a 3-digit number and get a 4-digit number. And that is 12 tokens long. Tokens, 12 tokens long, right? And basically, this is our max sequence length. And what this means is that we need to somehow pad every other sequence to be 12 tokens long, 12 characters long. And there are many ways to do this. Obviously, what first comes to mind from, maybe you had experience with transformer models, you might think that, hey, let's just pad on the right or pad on the left. But this won't be quite beneficial for us because if we think about it, there is a specific structure that arises if we look at these examples. We always have some number, A, we have a plus sign, then we have the second number, an equal sign, and the resulting number, right? All sequences follow this structure. And what transformers are good at is following the structure, not following the structure, but like keeping in mind the positions of each token. And what I'm talking about is that we always have a plus sign, then an equal sign, right? And we'll always have this number, and this number, in this specific order. This is important because what we could do is if we could somehow pad our sequences in such a way that plus sign and equal sign are always in the same place, token-wise, then our model could understand that, hey, number A is everything from the beginning of the sequence and up to the plus sign. B is anything that's between the plus sign and the equal sign, and C is everything that goes after the equal sign. So yeah, we would like to pad our sequences in such a way that plus and equal sign are always in the same place. But there's another thing. We need to learn. We need to teach our transformer addition, right? Addition. How can we do this? Because again, transformers are autoregressive models that predict token by token, right? So let's also define what is our prompt, what is our input sequence, and I think it's safe to say that this part is going to be always our input sequence, and we only need to predict the output number, right? So when we think about how we add up two numbers, let's take this example, 1 plus 1, right? Let me just copy it over. So 1 plus 1, well, it's kind of easy, right? We take 1, we take another 1 plus 1 is 2. Right, but let's take something more advanced, like 9 plus 10. We need to work with numbers that have different lengths. We have 9, which has 9 in its ones place, and we have 10, which has 0 in its ones place and 1 in its tenths place. So our model needs to be aware of the position of digits in a number. Which basically means that to keep our plus sign and our equal sign all in the same position for every sequence, and also make our model aware of the position of the digits in the number, we could pad numbers like so. So plus, okay. Oh, sorry. Take this equation, right? What I think is what I know, I already know, but still, what a good way to pad the sequence is leave 2 spaces, then a 9, plus, space, 10, and equals. The reason this is the best way to do it is because we allocate 3 tokens for each input number. And our model, since it understands positional, since the model understands positions of each token, it knows that this part is number A, right? And 9 is in its ones place. And here we have the number B, and 0 is in its ones place. And basically, the advantage of padding our numbers, our input numbers with pad tokens on the left is that our numbers, they basically always end up in the same place. I hope it's starting to make sense. Um, it makes it easier for our model to work with our numbers when it adds them up. A good example to understand this is, let's discuss how do we add up numbers as humans, right? Let's take an example with 9 plus 10, right? So 10 plus 9, same thing, right? As you may see, I align the numbers on the right for a very specific reason. It's because I start with uh, the numbers in their ones place, right? So it's going to be 9 because 0 plus 9 is 9. And then I don't carry anything. I don't carry a 1. And it's just 1 plus nothing, which is same as 1 plus 0, which is 1. And I get 19. And important thing that you might notice here is the order in which I, quote unquote, generate the numbers, right? So I start with writing out 9, and then I write out 1. And so, like in reverse order, as you may see. And this is important because we need to adjust how we work with the output number so that our model can predict the answer better. By that I mean it would be way more advantageous if we reversed the number in the output. The reason is, remember, transformer models, as any other transformer models or any other models in machine learning, they're stateless, right? So they don't keep any state. So when, let's say, we're working with an equation, right? 9 plus 10. Let's say we make our we force our model to predict the answer in the correct order, right? So 9 plus 10, it predicts a 1. Let's say our model is correct and it predicts a 1. Then it forgets everything. So the other part that the next step, the model sees this, right? Our input sequence and a 1 as an output. If you think about it, it doesn't quite make sense for the model to predict a 1 here, right? How can it get a 1, right? Obviously, it could, it could say that, we could say that, okay, it should be 1 because it's in the tens place. But what if our number was longer, right? Then this one and so this one and this one are identical, and we don't quite know which one are we working with here. So it is beneficial for us to instead write our answer in reverse. So if we predicted 9 here, and let me just remove this, our model would, again, it predicted a 9, then its memory is wiped, and now it sees this. Uh, what can it understand from this example, right? It sees that, okay, I write a 9 because obviously 9 plus 0 is 9. Then all I need to predict is nothing plus 1, which is going to be 1. So to mimic the same algorithm that we use as humans when working with when adding two numbers together on a piece of paper, we need to reverse the order of digits in the output number so that it is easier for a model to predict the number autoregressively. Also, we solve the padding problem because when our model is done predicting the number, in which in this case it's 19, if it's done predicting, all it needs to do is to fill the other numbers, the other spaces, because again, this sequence is 10 digits long, 10 characters long. All it needs to do is just predict two padding tokens. And in reality, it can just keep predicting pad tokens, right? Um, so yeah, so we pad our, what do we learn here? We should pad our input numbers so that they're adjusted to the right, right? So, and the length of the input numbers should be 3 characters long, and we fill empty spaces with spaces. And for output numbers, we reverse the digit order, and we place the remaining spaces are filled in with padding tokens. Okay, so this way it is always 12 characters long, and yeah, all sequences are going to be 12 characters long because over here we would predict 975 and then a space. Here we've already discussed. Here we don't need to we don't need to pad anything, but our output is going to be reversed. It's going to be 1991. Yeah, I hope this makes sense to you. Why do we pad this way and why we uh, reverse the output number? So I think when it comes to having to learn addition, we've discussed how we're going to do it. We've also discussed tokens, padding, vocabulary. We've already discussed, and I mean, it's just 12 characters long. The last thing is that we need to fit into the 10 million, 10 million size limit. Clarify about 10 million, and this is important because again, we can't exactly map into a 10 million parameter range, but we're going to come close. So let's discuss the architecture of the transformer model. I think it's we can take the original GPT-2 architecture as it is, but uh, we should understand that GPT-2 is much larger than 10 million parameters. It's like about 80 something million parameters. So we need to reduce its size. Let's draw the transformer architecture. So the first layer we have is positional embedding. No embedding. Then we have, let me just make the sizes. Yeah, perfect. Positional embedding. Then we have, sorry, not positional embedding, token embedding first, token embedding. Token embedding. Then we have positional embedding. Then we have positional embedding. Then we have multiple transformer blocks, and each block consists of layer norm, then multi-head self attention, uh, then another layer norm, then a feed-forward network. All of these are connected, and we have skip connections in some places, from over here to like bam, bam. Gonna be tough editing this, but I guess you understand what I'm trying to do here. Skip connection here, skip connection over here as well, right? Yeah, this works. And we have multiple blocks. Specifically, we have n blocks, these transformer layers, and transformer blocks. Yeah, perfect. And we have the unembedding token, unembedding. Basically, we call it unembedding. Unembedding, yeah. But you should understand that in practice, we are going to be reusing token embedding simply because I'm going to be reusing the same matrix because it's doing the same thing. We'll discuss this later during implementation. So what's important for us is we need to understand what's the size. Can we estimate the size of this transformer? And yeah, let's start with the embedding layers. So embedding layers, as you may or may not know, are just lookup tables. So in the case of token embedding, for every possible token, we have we have just a lookup table for every token. We have a vector size D model, right? And also should mention it here, just for here D model, because it's an important parameter when we're going to be calculating the size of the model itself. Okay, so these are just lookup tables. So for every token, we have a vector size D model. Same with positional embedding. For every position, in our case, we have 12 of them. We will have a vector size D model. Then comes layer norm. Also, one thing to point out, you may be asking why I have layer norm here, not over here. So why I have layer norm before the attention and the feed forward layer, why not after? Just because, again, I did some research and there's like this debate whether we should use pre-LN or post-LN. I think the original paper used post-LN and current implementations use pre-LN. I'm not sure which is going to be better in our case, but I think both are fine. So I'm just going to be using pre-LN because that's what I decided to use. There is no benefit to using pre-LN. You can just use post-LN if you want to. So with that out of the way, considering the size of our vocabulary, right, just 13 unique characters, our token embedding layer is going to be very small because all we need is a lookup table with 13 tokens with 13 vectors size D model. Same with position embedding. We have very short sequences, so these two layers are going to be very, very small. So, and we are going to be reusing the token embedding layer over here because the weights are going to be the same. This thing turns tokens into vectors, and if we transpose this matrix, we're going to have a matrix that we can use to turn vectors back into tokens. Layer norm is also very, very light in terms of weights. There are just some running statistics that are calculated. Sorry. So these layers are also pretty much free for us. So the only two layers we need to worry about are multi-head self-attention and feed-forward layer. So let's discuss. Okay, so for multi-head self-attention, as you know, in attention, we have three matrices. Can I make the text bigger? No? Okay. So we have the query matrix, and all these matrices are square. I should point out. Yeah, I think it's best if I just draw them by hand. So query matrix. Another matrix is the K matrix and V matrix. Also, we have another matrix, the output matrix, and I'll explain what it does when we'll be implementing the model itself. So we have four matrices, size D model by D model, D model by D model. We have three of them. Sorry, four of them. Right? And we also have n transformer blocks, right, times n as well. So our formula for multi-health self-attention is um, going to be n times 4 times d model times d model, which is just d model squared. Okay, this is multi-head self-attention. For feed-forward network, what do we have? We have, just a um, regular feed-forward network, like so, with one layer over here that does this connection, and another layer that does this connection. So 2 layers, so one layer over here, one layer over here, with input sizes D model into 4D model, or just because the original authors of attention is only need to use 4. They expanded the space into size 4D model. You can experiment with using a different number over here, maybe like 8 or 16 or 2 or 1. It's up to you, but we're going to pick 4. So D model, input features D model, output features 4 times D model, and another layer that transforms 4D model into D model. Whoop. Right? 4D model. Right? So the formula is going to be 2 layers. Well, I mean, we can write it out more explicitly. So D model times 4 times D model, yeah, times 2, basically, times 2. And this can be simplified into 8 times D model squared. 8 times D model squared. And remember, we have... Ooh, sorry, something broke. Second. Yep, perfect. And remember, we have n of those feed-forward layers. So the final number is going to be n times 8 times D model squared. So if we add these two formulas together, whoop, we have... Can I have an arrow, please? Yeah, perfect. N times n times 4 times D model squared plus 8 times D model squared, and I should put brackets like so. Bam. Yeah, like so. And as a result, we have n times 12 times D model squared. So yeah, if you plug in the original numbers for GPT-2 into this formula, so n is 12, D model is 768. You'll get something around 80 million, which is way too much for us, and we should somehow reduce the size. Obviously, we could use less blocks, but that's not going to cut it because our largest contributor is D model, because we're squaring it. What we could do is reduce D model, and so the original D model size is 768. And how can we reduce it? So now I'm going to discuss and explain multi-head self-attention. If you know what it is, you can skip. But basically, this was a mystery to me, like, where does this number come from? In reality, there is another parameter that we needed that we need to discuss. Oop, again, broke again. Which is number of hits, because as you should know, we're using multi-head self-attention, right? So we expect to have multiple heads. And what does it mean for our model to have multiple heads? And this is what I think is often missed in tutorials and educating videos. So our transformer, these matrices, what are key in value? These weight matrices are, in reality, are split into heads, like so. We get like a specific number of um, rectangular matrices, and the number is for GPT-2 is 12. So we split our weight matrices into 12 head matrices, and we do this like a virtual split. And the reason we do this is that our heads, uh, you know, we virtually split the matrix so that our heads learn different things about how to work with the sequence, right? So some heads might pay attention to the first and the last token. Some heads might pay attention to like triplets in the sequence. And basically, we are making so that we're letting our transformer learn multiple parameter analyzing machines. I mean, the explanation is kind of difficult to understand, but what I'm trying to get to here is it is better if our transformer learns multiple matrices, multiple of these small head matrices, instead of learning one giant matrix. And basically, since, as I've said, the original GPT-2 architecture uh, uses 12 heads, this D-model size comes from 12 heads times the head size, which is 64. Well, 12 times 64 is 768. And what we could do is reduce the number of heads. Let's say we reduce the number of heads by two, like by a factor of 2, and also reduce the number of layers by the factor of 2. We get 6 heads and 6 layers. So 6 times 64, we're going to keep the same head dimension, and it's going to be 360. Sorry, 84. It should be 84. Yeah, 384. Am I correct? 6 times 64. Yeah, 384. Perfect. So this will be our new D model. D model. Yeah, so we've reduced the number, let's review. We reduced the number of heads by 2 down to 6, and we reduced the number of layers from 12 to 6. So in this calculation over here, we will have just bam. So it's going to be 6 by 12 by, let me just write it out, 6 by 64 squared, which is 6 by 12 by 384 squared. And this is going to be 12 by 384 squared. Yeah, 10.6 million. 10.6 million. 10.6. And this number is quite close. I mean, yeah, why does it break so much? This number is basically what is required of us. So a 10 million transformer model. Again, these two layers in this particular case are free. The reason is our vocabulary is very small and our sequences are very short. Should underline this, I think. Yeah, our token embedding layer is free, positional embedding is free, layer norms are free. These two are the largest ones, and we've just calculated that the total size for them, in our case, is going to be 10.6 mil. So I think we are ready to implement the model. Yeah, we've discussed the sizing of our transformer model. We've discussed the architecture. We explored how we're going to train our model to learn addition. And I think we're ready to start writing some code. So for implementation, I'm going to be working on my local machine. You can use Colab. It's up to you. I'm going to be just saying that I'm going to be working locally. So we're told that we should only be using jax, flags, and optex, and we should generate a data set, yada yada. So I'm using UV for this. This is like a environment manager. You can use whatever you want. You can use pip. I'm just going to be using UV. So let me just initialize my environment. B312, and we're gonna need some dependencies, which are Jupyter, IPy IPy widgets. If you're doing this on Colab, you probably don't need to manage your environment. Probably everything is pre-installed, so you can just start developing IPy widgets. These three are for our interactive Python notebooks. Then we need JAX, Flags, Optex. We're gonna need NumPy as well. We're also gonna need EQDM for like nice status bars. And also we will need matplotlib uh, to plot our losses so that we can discuss our losses, just to discuss and to see whether our losses are going down or not. Yeah, this should be good. I'm gonna create a new notebook, 10 million model, find B. So I have all of the code on my right on this screen, but still I'm going to discuss everything and go through everything line by line. So yeah, let's go. First, we need to generate the data. And again, we're working with equations where we add up to 3-digit numbers, right? So should be quite easy. Have this array. What's wrong with my Python environment? Yeah, this one, please. Perfect. Does it work? Should be working now. Thank you. Yeah, perfect. So for a in range of 1000, this will iterate through every three-digit number, including 0. B, and then data end. So I could be saving strings right now, but I'm going to save this as a list of tuples because it's easier for me to work with, and I can transform this into strings later. So yeah, data is, as you can see, we have how many? We should have about 1 million. Yeah, we have 1 million tuples, 1 million examples. And the data set itself is quite small. So, you could think like, okay, let's train our model on everything, but this is not efficient and it's not fun because obviously then our model will overfit to this, to this what's it called? It will overfit to our data set, right? And I think our model is big enough to overfit actually, because again, we have only 1 million examples and 10 million parameters. I don't know how, but I guess we will overfit. Anyway, I know for a fact that a subset is going to be enough, and I'm taking 5%. You can experiment with it. One thing that you should watch out for is that there is like correlation between the amount of data amount of examples you train on and the number of epochs you use. So what I found is that if you are using less data, you should crank up the number of epochs. And if you use a lot of data, maybe you don't need as many epochs. So I'm going to be using 5% of the data, which is quite reasonable. Let me turn it into a NumPy array first. Array. Now let me import NumPy as well. as NP. I'm transforming it into a NumPy array just because it's easier for me to work with. Data, and let's take a look. This is just an array, ND array with shape 1 million to 3. Let's shuffle it. NP random seed 42. You could use any number, any other number. NP random shuffle X, and let's take a look. At X, yeah, it's shuffled. So now I can just take 5%, which I can just do by taking the first 5% of the data. So int len x times 0.05. And if we take a look at the train, it should be 50,000 examples, which is 5% of 1 million. Perfect. Okay. Now we need to tokenize and pad the sequence, and basically transform our tuples into actual strings and tokenize them and do a lot of other stuff. Let's define our vocabulary first. So we have digits 0 through 9. Every digit, every single digit, 7, 8, 9, space, plus, and equals. Here's our vocabulary. We need two hash maps that will map our tokens to their corresponding IDs and IDs to tokens, like token to ID and the reverse ID to token. Okay, token to ID is going to be, and here I'm using a neat trick with ticket comprehension. If you ever worked with tokenizers, I think you should be aware of it. So for KV in zip, vocab, range in vocab. So what this does, basically, we have a vocab, right? A vocab, oops, sorry, vocab. We have vocab, we have, and we would like to have an ID for each token. The easiest way to do it is to just generate a list of integers for this vocab, like so. We'll have like 13 integers. And what zip does, basically, it outputs basically it like joins two or more iterables into uh, like a matrix and goes row by row. So zip will return this, basically. You see, 0 is joined with 0, 1 with 1, plus with 11, and equals with 12. And here I just iterate over this thing, and I set that the first item, the first value is going to be my key, and the second one is going to be the value. So token to ID, we get a map where the key is our token and the value is our ID. And to make the inverse of that, it's quite simple. ID to token, same thing, V, K, but again, I flip them, right? KV in token to ID, items. Yeah, let's take a look. Bam. So tokens maps to their, IDs maps to their tokens. Now we can define a function that's going to tokenize our training data, tokenize and pad it all at the same time. Def tokenize and pad. As an input, we'll take this row, so I can just destructure it like so. I'll get A, B, and C are going to be these numbers. If you don't believe me, let's do just that. A, B, and C, train 0, and A, B, and C, bam. these numbers. Then I'm using one huge one-liner to make a string and tokenize it, but let's build it from the inside out. First, obviously, I need to turn these numbers into strings. String E. So now these are strings. And I need to, like, as you remember, I need to add spaces for the input run numbers on the left and spaces on the right for the output number. For that, I'm going to be using rjust and ljust. So for our input numbers, we're going to be using rjust. What it does, it adds, return side right justify string of length width. So our length width is 3, and the filling character is going to be space. And we're going to be using space as our padding token. So let's, for example, take these two numbers, like this equation, like 1 plus 2 plus 1 plus 2 is 3. And as you can see, we're padding our numbers correctly. We had spaces on the left. So for C, we need to reverse this and pad with padding tokens on the right. So let's say we have 1, 2, 3 here. We need to reverse this. We can do this with reversed. Yeah, we need to turn it into, it's going to be an iterable. We need to turn it into a string, like so, join, bam. And we need to use ljust in this case to adjust it to length 4. You can see we added a space over here. Now we can just use an f string, turn this into an actual string, equal sign, did not terminate the string, like so. And we need to tokenize this. So to tokenize, we're going to be using our hash maps, our dicts. So for that, we're going to be using the map function. It takes in some function and goes through an iterable, and string is and the string can be iterated through. So we're going to be using token ID get for this. And with a map object, and we're going to turn it into a list. And as you can see, we've done it. So this is our tokenized sequence. It's kind of hard to see, but if we look at token to ID, we see that 1 should be turned into 1, and we can see that spaces that we have 2 of these spaces, right? They have ID of 10, and yeah, right here we have 2 spaces marked with 10. So 10, 1, 11 is plus, 2 tens, 2, 12 is the equal sign, 3, 2, 1, and space. Perfect. So let's just take this function, this one-liner, and put it right here. Return, bam. And now let's just tokenize our training data. Train tokenized. And there are many ways to do this, but I decided to use this thing. So apply along axis. We provide a function, token is in pad, the axis index, which is going to be 1, because we want to do it row-wise, not column-wise, and train. Let's look at train tokenized. We get it in the array of 50,000 to 12. Perfect. And now we can, yeah, we can now work on the architecture of our model. So, let's go. We're going to work with flags. So I'm a PyTorch guy. I'm not flags, jacks, optax guy. Basically, flags is like a special library that is used alongside jacks to define neural networks in a way that's similar to PyTorch. You're going to see the syntax and it's going to look quite familiar. So how do we do that? We need to import from flags, import nnx, and you know, Basically, Flex has two APIs. One is the old one is the new one. The old one is Linen, but it's still used to this day because a lot of code depends on it. The new API is NNX. Feel free to use whichever ones you like. I just decided to use the new one for no particular reason. Just thought like, yeah, let's use NNX. Yeah, and also let's import Jax. And I didn't explain it, but Jax is basically NumPy plus AutoGrad. Yeah, and this is like a library that allows you to do a lot of parallel computation and all this useful stuff that's useful for neural networks. Again, go through Jax tutorials over here. You're gonna see a lot of, you're gonna, learn Jax much better if you just go through the tutorials. They're quite short and easy to understand. But for today, I'm just going to be focusing on how to use these libraries like Jax, Flex, and Optex. And if you have any questions, again, look it up and go through the tutorials. Okay, so let's define our transformer. Plus transformer, former. Syntax should be familiar if you've ever worked with PyTorch and NX module. Now, the init method. Init. So we should provide some things into our transformer, and the parameters that we should provide are D model, obviously. By default, is going to be 384. Number of layers going to be 6. Number of heads is going to be 6 as well. Also, we need to provide vocab size, which is going to be 13, and max sequence length going to be 12. Also, we need to always provide a special parameter called RNGs, NNX RNGs. So I'm not a professional in this ecosystem, so RNGs is basically a way to define the random seed. Yeah, just to manage RNG state, as you can see. It is required, and basically it is used to provide the same random state to every training run in your code. Basically, just keep in mind that we always need to define RNGs in our init methods, and when we initialize our modules, we also need to provide RNGs. So let's go. Let me just save these values to my object, like, oh, like so. Bam. Oh, thank you. Let's define our architecture. So over here, remember we have token embedding, positional embedding, and then a few blocks. So let's start with embedding layers. Self-token embedding. We're going to be using the included embed module. So number of embeddings will be 12. Sorry, will be vocab size, actually. And features is going to be the model. Actually, I can just, that's fine. The model. So again, we'll have vocab size vectors of size D model, which is going to be 13 vectors length D model, which is 384. And we pass an RNGs over here. RNGs. Same idea with positional embedding, sequence length. And now we need to define the transformer blocks. And here, usually you'd see for PyTorch codes, we just use list comprehension. And we can do the same here in flex, but we need to wrap it into an NX list, like so. For nothing in range of number of layers, we will produce transformer blocks. We will pass RNGs into there always, and also we'll provide demodel, demodel, and number of hits. Hits, number of hits. Yeah, let's define transformer block. I'll implement the call method later, the end, but keep in mind that we'll cover it, of course. Transformer block, NX module, right? So as you remember, layer norm, multi-head self-attention layer norm controller network. So let's go def init self, and we're passing the model and what else? Number of hits, then RNGs, these and these. We need two layer norms, multi-head self-attention, and two linear layers for feed-forward network. Self layer norm 1 is an NX layer norm. We need to provide number of features is going to be D model, and we need to provide RNGs. Same for layer norm 2. Now for attention, you can use multi-head attention over here. I decided to implement it myself because it's way more fun to do attention yourself. And also you'll have code that you can edit if you want to try different attention implementations. So I'll implement it myself. Yeah, so layer norm, and now fully connected layers. Yeah, fully connected, and the next linear. So input feature is going to be D model into 4 times D model. The second layer is going to be reverse 4 times D model and D model. Cool, and I need to pass RNG. For attention, we're going to provide D model and number of hits and RNGs. And we'll cover the call method later. Let's implement attention. If you know how to do it, go ahead and do it. Or maybe you're going to use NX multi, like the built-in attention. It's up to you. If you don't know how to do attention, I'll explain just now. But if you don't want to watch this, you can skip. So class attention and NX module. Sorry, module. Define init self D model, number of hits, and RNGs, and NX RNGs. So for attention, we need 4 matrices, right? Size D model, self W, we need weight matrices, WQ, and NX linear, D model, they're square, so D model by D model. We don't need no bias, false, and pass our 4 of these, they're identical, WQ, WK, WV, and WO. And let's save number of hits, like so. Let's define the call method. So self, and we expect some X, and X is going to be a Jax array. So here I want to dive deeper into how do we work with tensors and other stuff, because to me it was not obvious. So if you know how to work with tensors and you know the answer for the question what's going to be the size of x and why it is why it is the way it is, right? You can skip, but for others, let's discuss. So what is often, when attention is explained, usually this formula is covered, right? Softmax, query, key transpose, square root of d model times v. And I find this completely unintuitive. Because what is key? What is q? What is k? What is v? Why do we divide by this? What is softmax? And why do we have weight matrices here? Why are they not this? Right? So uh, let's start. Basically, the reason we have W matrices is because to get WQ, WK, to get Q, K, and V matrices, we're performing matrix multiplication. So we take our X and we matrix multiply it by Q and by K and by V. Let's do just that. To do that, all we need to do is just write self W Q times X. All it does under the hood is just X matmul WQ, right? And it would do the same for all of these matrices, except the output matrix, because we're going to discuss it a bit later. It is not used for tension directly. Yeah, but we're going to talk about it. Now, what about the shape? Let's think about it. What is often covered is that we discuss an example with one sequence, right? And if we're talking about one sequence, it's simple. As an input, we take a sequence of size t. A fixed size. We already padded our sequence. It is always the same length, and in our case, it's going to be 12. So our input here is a sequence size t, and in our case, t is 12. Then it passes through the embedding, and now here we get, for every token, we get a matrix. We get a vector. So the effective size is going to be t by d model. T by d model, right? After positional encoding, positional embedding, uh, the size remains because we just add these two together. So nothing special here. We just add these two together like so, right? Same size. Now, when it goes through layer norm, multi-head self-attention, feed-forward network, same thing happens. We just get the same, same sizes, T by D model. And we unembed, we get back T again, right? So these are the sizes that we're working with. Now, if we were to train the model sequence by sequence, right, where we're going to be feeding the entire 50,000 data set of length 50,000, right? It's going to take a while, right? And processing sequences through the model is, it could be parallelized, basically. The reason is processing every sequence does not depend on any other sequence. So again, we can parallelize this process. That's why often we add a batch dimension over here. And what that does is basically, we do the same process for every sequence in a batch. So like 2 sequences at once, 30 sequences at once, 5,000 sequences at once, doesn't matter. But what's important is that we're working with sequences, right? So now we get these sizes, and should understand that all this thing does is basically perform the same operation for every sequence, but for all sequences in a batch. Okay, hope this makes sense. Um, okay. Uh, okay. Now, when we're working with tensors over here, right? Um, we are performing matrix multiplications. So we know from this that the size of x is going to be d by t by d model, right? So size of x is going to be, where is it? Size of x is going to be b by t by d model. Q is d model by d model. Q, K, W, Q, all the weight matrices are square. D model by D model. How does that work? This thing has like 3 dimensions. This thing has 2 dimensions. How does this work? So basically, under the hood, we add a ghost dimension. Because in reality, all we need to do is apply the same matrix to all these other matrices. So the sequence matrices, we apply the same matrix. And this dimension serves as a batch dimension. So we could say that, yeah, here I should have added W. Yeah, be correct. Yeah. So the sizes over here are going to be D model by D model. D model by D model. Now, how do you perform matrix multiplication for tensors? Like, how does this work? Because, for example, in my case, during university, we always worked with like 2D matrices, like size 2 by 3, then matrix multiplication 3 by 5 something, right? And we always knew that for matrices A and B with these sizes, the resulting matrix C will have the dimensions of 2 by 5 because the rule was we cross these, the inner dimensions out like so. And those dimensions that are left, which are 2 and 5, are going to be the new dimensions for the matrix. This is how matrix multiplication works. But how do we do it here? Like, what's going on? The rule is basically the same, right? But we're only working with the last 2 dimensions. Last 2 dimensions. So forget about B for now. And for the matter of fact, we could have as many dimensions as we want over here, just so long as we have the same dimensions, the same batch dimensions uh, in the second matrix, right? So let me just move this. Bam. Right. So as long we can like mentally divide the dimensions like so. So these are the actual like matrices we're working with, and these are the batch dimensions. So basically, whatever operation that's happening with these 2 matrices is going to be repeated for everything in the it's going to be repeated across batch dimensions. So let me just reduce the sizes like so that's easier to understand, to visualize. So we have T by D model, so 12 by 384 matrix. Yeah, like so. And we have multiple of them, right? We have, say, our batch size is 4. We have 4 matrices, right? So B is 4. B is 4. And here we have D model by D model matrices, which are going to be like so. And we are repeating the same matrix multiplication operation in pairs. This matrix is multiplied with this one with this one, this one with this one, this one with this one, right? And we're just batching this operation across the batch dimension. I hope this is clear. Because the reason I need to discuss this is because the next step is going to be splitting uh, the the weight matrices, these guys, into heads, right? Like so. And we know that basically, each head should be some size, but basically we want to have n heads, right? We have n number of heads defined, and we want to virtually split the matrix into heads. How we can do this is with reshaping. So again, for W, Q, K, and V, the dimensions are B times what? Times D model by D model. We can perform a reshape to reshape it into a new shape, which is going to be B by D model. Is it? No, sorry. Sorry. Yeah. Sorry. We're not I made a mistake. We're not reshaping the matrix itself, we're reshaping the output after matrix multiplication uh, because yeah, let me just cover this. So we perform matrix multiplication over here, right? So WQ times X times WQ, and we get the new dimension is going to be B by T by D model. Because again, these two dimensions cross out and we get T by D model. Perfect. So these are our Q, K, and V matrices. Now, when we compute attention, uh, only then we need to split our matrices into heads. We don't need to do this when we're working with weights because we don't want them to be split so that we can parallelize matrix multiplication. When we're computing attention, then we need to split. So to split the result into like specific number of heads, into 6 heads, we're going to perform reshape, which is going to basically reshape it like so. B by T by number of heads. Let me just write NH. And the head dimension, HD, which is 6 and 64. And we split 384 into 6 and 64. Perfect. And let's do just that. So reshape. Let me just get the dimensions from our input matrix, like so. And now I can easily reshape B by T by self number of heads by, let me compute the head dimension. Head dimension is going to be D model divided into self number of hits, and I perform the strict division because I want to get an integer over here. I don't want any floats. Head dimension. Perfect. So now the size of this result is going to be B by T by number of hits by head dimension. But when we're going to be working with the formula for attention, right, we'll have the same size. Right? We're going to have this size. And remember the rule, when we're multiplying, we're only working with the last 2 dimensions. And it kind of doesn't make sense to work with number of heads and head dimension sizes, right? We want to work with the token dimension and the actual attention dimension. So we want to swap these 2 dimensions so that number of head dimensions becomes the batch dimension, right? It moves to the left. And the sequence length dimension goes to the right, so we can actually do matrix multiplications. To do that, we perform a transpose. And for transpose, basically how it works, imagine our dimensions are zero indexed. And in transpose, we define the new order of our dimensions. And since we want to basically keep this dimension in place, keep this dimension in place, and swap only these two, all we need to do is to write 0, 2, 2, 1, 3, right? Because this one's going to be in place, right? We're not touching that. The last dimension is kept in place, and we swap these two, so it's going to be 2, 1, right? Perfect. Okay, now we can actually perform, like, do the attention computation, right? This bit. First, we're going to multiply Q by K transposed. Of course, Q by matrix multiplication Q, K, and I can't do this T, this transpose, because this transpose basically reverses the order of the dimensions. And in my case, basically, it's going to be that dimension. Let me just swap these two around first. Quickly, it's better if I just so number of hits. My handwriting is terrible if you didn't notice. Number of hits and T, right? And that capital T is going to transpose dimensions in the reverse order. So I'm going to get head dimension T, number of hits, and B, which is not what I want at all. I would just want to swap these two last dimensions. And for that, I can use transpose again. I want to keep first, second dimension and swap the last two. So 0, 1, I'm not touching those. I want the last dimension to become the second dimension and the second dimension to become the last dimension. Like so. Now let's normalize. Here we normalize not by D model, but by, since we're working with heads, we need to normalize by the size of each head. So in this case, normalized like scores, going to be scores over head dimension raised to the power of 0.5, which is the same as squaring it, but raising to the power of anything is faster than taking a square root. Right, so after we did this, so let's look at the dimensions. What we'll have is this, yeah, we'll have is this. We have, this time, this matrix multiplied by B, number of hits, head dimension, T. We're working with the last two dimensions only. So we cross this out and we get B, number of hits, T by T, the square matrix, this thing. Right now we need to make it, we need to zero out this upper part, because basically this represents attention for future tokens, which our model should not see. And we can do this by applying a mask. Basically what we want to have is that after softmax, before we multiply by V, we want everything here to be zero. 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. Want everything to be zero over here. And how to get uh, zeros in softmax. If we put negative infinity, we'll get just that. So we want to make our normalized scores matrix. We want to make it so that all of these scores are negative infinity. We can define a mask and apply special mask. So let's make the mask itself. For that, we will use Jax. Let me just import Jax NumPy as JNP. So JNP triangular lower. And this shape is the matrix itself is going to be JNP ones. The shape is going to be T by T. But what happens is we make the matrix of the same size as our attention scores, right? Like these scores, the scores that we get in this part, right? And we get the same matrix. It's going to be upper lower. What this means is that over here we get like matrix of ones. It's going to be a square matrix of ones. 1, 1, 1, 1, 1, 1, 1, 1, 1. Then we apply the upper lower function, which replaces everything above the main diagonal with ones, and that means we effectively get zeros here, 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 and here, right? And now we get a mask. If we apply, we can treat this mask as a Boolean mask. Whoop. A Boolean mask, and imagine that ones are false. So ones are going to be false, 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 and zeros are going to be true, 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 true. And if you remember, this mask corresponds to our original mask, the normalized scores, right? We can use the method called JNP, where, let me just start typing this out. Let me just get the masks. Yeah, let me just start. JNP, where we apply a condition, which is going to be our mask. We provide the matrix that we're going to be working with, which is going to be normalized scores. And we provide the value that we want to replace. We're going to replace according to the condition, which is our mask. And in our case, it's going to be JNP negative infinity. Right? So what will happen basically, everything above upper triangular, everything above the main, everything above the main diagonal is going to be turned into negative infinity, because according to the mask, we get trues, right, for every position. However, this code won't work because the size of our mask is just T by T, and for normalized scores, it's, if you remember, B by number of hits by T. And we can do this indexing trick where we add ghost dimensions like so. So first two dimensions are going to be the ghost dimensions. And basically we keep the other dimensions like so. Yeah, if you are confused about sizes or anything like that, feel free to debug. To debug, all you need to do is just attention, 384, 6 hits, and we provide RNGs like so, and the next RNGs, and we need to provide some number like so, and we pass in some matrix X. So X could be Jax, random, normal. So for key, we need to generate a random key. And we do this like Jack's random PRNG key. We provide any seed, could be 0, could be anything. And we provide a shape. And if you remember, it should be like batch size by T by D model. Batch size could be anything like 2, T is 12, D model is 384. And you can debug like so. So let me just find attention. And now I can, whoops, NP is not defined. Cool. Attention, bug cell. Yeah, we dive in. Let's say I want to look at normalized scores. Bam. And I can get like scores, shape, a, yeah. So you can just look at the shapes yourself if you don't understand what I'm talking about. And this is what I did when I was implementing this thing. So I highly advise you to do just that. Perfect. GNP where? Masked scores. Scores. Okay. Now we basically, where is it? We did this, we normalized, now we applied the mask. Now we need to use softmax on this thing. So softmax going to be Jax and then softmax masked scores. Now all we need to do is just multiply by V. Softmaxed, sorry, attention, going to be softmax times V. Oh, done. Now this WO matrix, basically when we do attention, all we do is calculate the scores, and we need to somehow interpret these scores and use them down the line. This is where WO comes in. It mixes up the signals in a way that's interpretable down the line in our model. So we need to basically just pass the results of attention through WO. WO attention. But you should remember that the shape of attention is different right here, and we can actually check it. Let's look. Let's use debugging. I just deleted the code, so okay, 1 second. Can I? Oh, okay, let me just quickly repeat it. Jax, random, normal, X, random, PRNG, shape is 2 by 12 by 384, and attention 384, 6 by RNGs, NX RNG, and that's in X. And let's debug the cell, and we'll take a look at attention and the shape of attention. Attention shape. So it's 2 by 6 by 12 by 64, which is batch size, number of hits, sequence length, and head dimension. WO shape shape. Uh, yeah, it's a special object, so basically it's gonna be a square matrix, right? We can't quite work with WO because if I do this, I'm gonna get an error saying, yeah, it requires constraint dimensions to be the same shape, got 64 by 384. We need to undo this thing that we did here, so we need to transpose back and reshape. Let's fix this. Let's transpose. Let me just do it here. So attention shape, attention shape. Let's take a look at the shape. Let's transpose. Do I need to, transpose. I need to swap the middle dimensions. So I keep the first one, I keep the last one, and I swap these two, 2 and 1. 2 and 1 shape. 2 by 12 by 6 by 64. Perfect. And I need to reshape. Reshape into B by T by D model. To join the heads back again. Get the shape. Bam. 2 by 12 by 384. And I can actually pass this through W. Oh, let me get the shape. Oops, shape. Bam, everything works. So no errors. So let me just take this and apply it here. And this should be it. Yep, this is attention. We did it. Congratulations. We did attention. Okay. Now let's work on the transformer block. So here's going to be pretty simple. We also accept X, Jax array. And the shape of X is going to be, as we've discussed, going to be this, D by T by D model. We need to pass it through layer norm, then through attention, through layer norm, and through feed forward layer. Also need to perform some activations, but we'll do that in a minute. So first layer norm, so layer norm 1, X. Now, after layer norm, we pass it through attention, so self attention. Bam. And don't forget about skip connections. So X equals X plus attention. Now H, no, actually, now pass it through layer norm again. Self layer norm 2 X. Pass it through layer norm. Now pass it through the first feed forward layer, FC1. Self FC1 this. Now we save it and we need to actually pass it through an activation function. And I'm going to be using RealLoo for this. Simple and easy. You can feel free to use any other function. I'm going to be using RealLoo for this. And now the last step is to just add a skip connection and what? Yeah, and pass it through the last fully connected layer, self fully connected to H. Bam. You can do it nicer, like so. Perfect. So this is the transformer block. Everything's defined here. Let's do the call section for the call function for our transformer. Here also accept X, which is going to be a Jax array, and the dimensions here are going to be T by T. X is going to be self. No, actually, let me just write it like so, bit by bit. Self token embedding. We pass in X, and we get for every batch. In every batch, we get a matrix size T by D model, and also we add positional embedding. Here, instead of passing X, we need to pass in basically a range of numbers from 0 to 12. And this is a way to do, because again, we're working with positions, not tokens themselves, and positions don't change, right? So instead of passing X, we should pass an array of 12 numbers. The easiest way to do this is chain P arrange X by shape -1, which basically takes the last shape, which is going to be the token sequence length. So if we ever decide to change max sequence length, maybe you want to do up to 4-digit numbers, right? We can just change this and don't change anything here. Yeah, but this basically returns this. We had 12 here, right? An array, and we're going to return. So we take positional embedding bam. Max sequence length is going to be 12. The model 384. RNGs is NX RNGs 0. Pass in the range. Get the shape. Yeah, 12 by 384. Cool. I think it's cool. Okay, let's save this. And now we need to pass the results through our transformer blocks. For that, we do for block, block in blocks. H is block through H, self blocks, self blocks. Now we've passed our data through our transformer blocks. Now we need to unembed, and I've said that we're going to be using a technique called weight tying to reuse the same weights. Basically, again, this matrix has shape 12 by 384, and if we transpose it, we get 384 by 12, and does, let's write it down, 12 by 384. And if we transpose this matrix, we get 384 by 384 by 12, which basically would do the inverse. It would convert IDs back into tokens. Sorry, vectors back into tokens. Okay, to do that, we would just do matmul self token embedding, take the matrix itself and transpose it. We're gonna get, these are gonna be logits. And let's return logits. Cool. We did it. Now we are ready for the training step. Okay, so let's get a training. For that, we're going to be using Optext, the last of our libraries. We're going to be using RNGs a lot, so let's define them right here. RNGs 42, you can use any other number that you want. So let's define our model. Model, transformer, we're going to be using defaults, so RNGs. And let's use an optimizer. Let's define an optimizer. There. And there's it's an interesting way of defining an optimizer. In Optex and Flax, basically you do an NX optimizer. You provide a model, and then you define gradient, an Optex gradient transformation. Basically, you can define whatever gradient transformation you want to do. If you're correct, you can define your own. Maybe you want to do custom Atom, some kind of other transformation that's not available by default. I'm going to be using Atom. But again, you can do whatever you want. Yeah, and now we need to define with respect to, which basically tells our optimizer what parameters to optimize, and it works like a filter. Since we want to optimize every parameter, we're using an NX param. This will touch every parameter in our model. Cool. Transformer block is not defined. Cool. Transformer block, transformer. Yeah, cool. So now let's define the loss function. Def loss fn. It accepts a model, the NX module, and batch x, which is going to be a JAX array. Cool. We pass in, need to get logits from our model X. Now, if you know, you know. But basically, when training transformers, our task is basically next token prediction, right? So we have this sequence. Let me grab that real quick. we have this sequence, and we would like to predict. So for this bad token, we would like to, since we're predicting the output, we would like to predict. Let me just align it properly. Or if this is our input, then like so, yeah, like so actually. So we would like to predict after. So say this is our input. So say this is our input. Not this is our input, and we would like to predict after equal sign. We would like to predict 9. So that's why we shifted on the left by 1. And in reality, we're actually going to be shifting our input by 1 on the right. By that, I mean we're just going to cut it off over here, like so. And we're actually going to cut off this bit over here, like so. To do that, our predictions are going to be logits, but shifted by 1. And our labels going to be x, but shifted in the other way. Now we get the per token loss. Token loss. And for that, we're using, as usual, cross entropy. Optax has a neat function for this. Softmax cross entropy with integer labels. We pass some predictions and labels. Cool. Now we need to compute since we're working with batches, we need to produce batch loss. For that, one thing that we need to consider is that we don't want to compute losses for our input sequence, right? We're only interested in the output sequences, right? We want to compute the losses for the output sequence. So we would like to zero out losses for every single token in the input sequence. We can apply a mask, loss mask. Basically, it's going to be 8 zeros, 8 zeros, and 4 ones, because our input length is 12, and we're only interested in the last 4 tokens, right? Right. And we also need to shift it, turn it into an array first. Chain the array, and we need to shift it as well by 1 so that it aligns with like this part. Now, to compute the batch loss with respect to our let's to compute the loss considering the loss mask, all we need to do is per token loss times softmax, times loss mask that we've used. We've defined, we'll get the sum, and we divide not just by the batch, but also by loss mask sum times batch dimension 0. So yeah, cool. This is our loss function. Now let's define the training step. For that, just do that train step model and NX. Again, if you don't get what the hell is going on here, you can take this function and just provide your model, provide your fake batch, and go through why it is the way it is. This is why I love Jax, Flax, and Optax, because it's quite easy to quickly make a we're just working with functions. We're not working with huge classes that we need to initialize properly, stuff like this. So yeah, this is quite cool. So model optimizer, the next optimizer, batch, sorry, checks. Cool. We need to use NNX JIT for this. Read up what JIT is in the JAX tutorials. I'm gonna explain here, but basically it is required for us. Now to compute the gradients that we're going to be using in our optimizer to optimize the weights of our model, and then Flax provides a full function called value and grad. It's basically a decorator. We provide our loss function, and now we call it as usual with the same parameters as our loss function model and batch. We get loss and gradients. We pass gradients to our optimizer, update model and grads, and we return the loss. Cool. Now we're ready to write the training loop. So for batch size, our sequences are quite small, so we can use a large batch size. I use 256. For number of epochs, again, it's up to you, but I decided to use 10. You can always increase or decrease this. Yeah, let me import EQDM. EQDM. And let's write the training loop. The losses. I'm going to save all the losses so that we can plot them later. For epoch in range epochs. Now we need to basically split the training data into batches and process it batch by batch. One thing is, it's preferable if we mix up the batch itself. So yeah, and like we mix up the batch itself. We mix up the training data once again, so that our model doesn't learn, that our data doesn't learn the sequences within our training data. Even though we've shuffled it before, we want to shuffle it again here. So let's do just that. I use a different way here, but basically you could use, I think it's safe to use NP, not NP, GNP. Oh. There, shuffle. Ah, yeah, that's the reason why I do it this way. No, wait, it's not GNP, sorry, NP random shuffle batch. No, wait, that's not going to work because it's going to shuffle the same way each time. So yeah, this is why we need to use permutation indexes. So let me just write the loop first. For I in TQDM, I'm just wrapping the range. We need to provide number of batches. Let us compute this. Second description, simple description showing on what epoch we are. Epoch. So number of batches is going to be length of our train, tokenized, batch size, batch size was not defined because it isn't. Cool. Batches. I'm getting tired, as you can see. So batch is going to be train tokenized I times batch size, yes, and I plus 1 times batch size. Yeah, and now we need to use our training step, model, optimizer fetch, get the loss, save the loss, then load loss. Cool. Now, one thing to do here is this is going to be an ND array. First, I need to pass it through GNP array. Also, this, as I've mentioned, we need to shuffle this. So let me just replace it with shuffled. And to shuffle properly, shuffled will rely on train tokenized and provided a permutation index. Gonna make which we're going to make right here. NP random permutation length tokenized. Cool. We can start training. Something went wrong. 64 by 384. Something's not right. The training step. Okay, I goofed up somewhere. Model dimensions. Maybe I didn't reshape. Probably I didn't reshape. Just do my code again. Interesting. Let's tackle this bit by bit. So this is definitely something wrong. Let me just rerun our code. Maybe I didn't run some cell or something else. Yeah, it was just I needed to redefine all the blocks, all the modules. Cool. It's training. While it's training, let's write some code to print out the losses. It's gonna take a while. For me, it's about 40 seconds per epoch, so it's going to be about 10 minutes. Let's go import import matplotlib by plot sp and just plot the losses. Right, plot this. Plot x label tip y label loss. And once training is done, basically we'll print out. Now, next step, we can start working on it right now while it's training. We would like to actually test out how the model works. Have it learned math or not? Basically, the simplest way is to make a prompt and provide it to the model and see what do we get. So let's make a prompt. I'll just manually pre-tokenize it and prepad. So let's just do 1+1 for now. Obviously, you can write a simple function that takes in a sequence and returns tokenized and padded token sequence. But I'll just do it manually here. Now, tokenize. We need to use, we can use map and then turn to an NP array, but I'll do it using NP vectorize. Basically, we provide a function, and in our case, it's going to be token UID get. We apply this function on prompt. The shape is going to be just 8, but we need to add a batch dimension. So to do that, we use this trick, indexing trick, add a ghost batch dimension. Now, we only need to generate 4 tokens. So let's do just that, tokenized prompt or range 4. we pass in the sequence to the model, get the logits. Now, to get the next token, we take the last logit. Again, the first dimension is the batch dimension. We take the last logit. Then we use JNP argmax, get the index of the largest of the index of the largest logit, which is going to be our token ID. Logits and the access -1. 1. Next token, this, and we need to update our sequence by tokenizing JNP, concatenate, sequence, and next token. Remember, we need to add. So in this case, batch dimension already exists. We need to add a fake dimension for length. We index it like so. This one. And we're going to get a sequence, and to undo the tokenization, we can do just vectorize. Here we're going to use ID to token, get sequence. And yeah, once this thing trains, and it's almost done already, once it trains, we're going to get sequence. While it trains, I actually want to discuss why I think this exercise is amazing. Because compared to other exercises that basically involve repeating the GPT-2 architecture and just checking that weights are the same, cool, there's nothing you can do after that. So once you write out the architecture, you just get the model, and yeah, you learned the architecture. Congratulations. But there's so much to learn other than just the model architecture. Like, how do you train it? How do you do this shift thing, right? How do you compute the loss? How do you work with losses? A lot of stuff, right? So how do you generate? You should write your own generation loop. There's a lot of stuff to do. So this is why I love this exercise, because it forces you to implement everything, starting from like data generation even, right? And if you do your own attention, if you do your own transformer, you can then later try different architectures, play around with model sizes. Like, what if we had less layers? What if we had less hits? One interesting thing, does this thing work with 4-digit numbers? Does it generalize, right? Spoiler alert, it does not. So you can implement your own attention. There are a lot of different, you could try working with KV cache. You could implement KV cache, but you're not going to see any difference, if you're not profiling. Maybe implement KV cache on regular models, but still, you can implement your own attention, right? The like DSA, DeepSeek attention, grouped query attention, some other types of attention. Pretty much everyone nowadays implements their own version of attention, and you can too. Also, just pull it up, lad. Also, remember that Vlad here says derive chinchilla loss for this. This is basically what I'm going to do in the next video. So basically, he mentions MOE architectures. One thing you could do is have it learn subtraction, division, multiplication, and train it with like 4 experts and see which expert is activated when. Also, you can do mechanistic interpretability on this thing and see how does it do addition. How does it do any other operation? Uh, and it is interesting because, technically, uh, all the model needs to do is to define like lookup tables on how to add up 1 plus 1, 9 plus 1, and other combinations, and then just apply these lookup tables. And this is exactly what transformers do, right? They do attention, and then in the linear layers, they just extract the knowledge that they need, right? So yeah, almost done. It is done. Bam. The laws converged, and we got 2. Perfect. So let's try a harder example. Yeah, let's do 9 plus 10. Will it output 21? Moment of truth. Bam, bam, bam. No, it's going to be 19. Perfect. What about 1, 2, 3, 4, 5, 6? 579, which is correct. What about 999? 999, 9, 1998 is correct. So yeah, once again, the code is going to be in the description, and if you followed with me, so like feel free to, you know, work with this code, do whatever you want, explore, learn, have fun, right? This is what we're here for. And yeah, I hope you enjoyed. See you in the next video where we're going to be discussing chinchilla laws and other cool stuff. See ya.